In this video, I'm going to go over how to utilize Yolov8 for single animal behavior analysis. So let's go ahead and open our Anaconda and make sure our training videos are in a folder. And on the right, I have a text file with some of my notes from where I'm going to copy paste some of my codes. And I will also put this text file in my video description so you guys can all utilize it. So first thing, I'm going to go into the folder that has my videos. And then I'm running the code snippet to extract 20 frames from the video of my choice here. And I'm utilizing open field video. It's a 30-minute video to use as a training example. Next, I need to make a folder and label it images and move the training images into that folder. So a couple of libraries need to be installed. One of them is pip install LabelImg and pip install Labelme. But before I do that, I'm going to activate my YOLO test environment. And within that environment, I'm going to install these. I have already installed these previously. So for me, requirements are already satisfied. But I'm running through the motions anyways, so you can see how to install these. So with that out of the way, let's open up Labelme. And the way to do that is just type in Labelme. I'm opening the directory where my images are saved, and then I need to make sure I click on the automatic save and change the output directory. Here I'm going to create a new folder and call that labels. So one more time, I'm making a new folder inside of my images folder and calling that labels. And this is where all of my labels are going to be stored. I'm using Create AI Polygon tool. It's an efficient SAM model. It automatically allows me to pick out the mouse from the background and speeds up the annotation process. Now, of course, you can always create more than one annotation for multiple things in your field of view. For example, if you're doing 2 animal experiments, you can utilize annotations for both of your animals. This way you can just label one as mouse 1, the other one as mouse 2. Okay, so that is done. I'm just checking all my labels are there. I'm going to now go ahead and bring my labels folder outside into the root directory of my folder. And I'm just cutting and pasting it from the images folder out to the root folder. Next, I need to create another folder and put the images and labels folder inside of that folder. And this folder is going to be called test. I'm creating another folder. This folder is going to be called dataset. And my test folder is going to go into the dataset folder. So here I have a couple of nested folders, with dataset being the main folder. Within that is the test folder, and inside the test folder are the labels and images. Next, I need to install the Labelme to YOLO to convert the labels that were created using Labelme to the YOLO format so that we can utilize them with YOLO training. Here I'm going to convert my labels to the YOLO format by typing in Labelme to YOLO --JSON and then the path, but I think, yeah, I mistyped. So it's Labelme to YOLO --JSON_dir and the path to the test folder. And it's really fast to convert the labels to the YOLO format. And then this new folder comes up, which is called YOLO dataset. And this folder now contains the training dataset that we would need, and also the labels. But in order to utilize this for YOLO training, we need to move some of the files around. And here you can see what I'm going to be doing. I'm going to move this folder out, the YAML file out to my main directory. Then I'm going to create a couple of other folders. Actually, this should be train, not test. Then another folder is going to be called VAL. So within the YOLO dataset, these folders have the YOLO formatted labels and images. So from the dataset, I'm going to move the images to their designated train and val folder in my root directory. All right, so the train folder is completed. Let's move on to the val folder here. So same thing for the val folder. I'm going to create a folder called labels and a folder called images. And I'm going to move the labels from the val folder inside of the dataset, YOLO dataset folder, to the root directory val folder. It sounds complicated, but once you do it a couple of times, it becomes easy to understand. So now the YOLO dataset folder is empty and I'm deleting it. Okay, so the dataset.yml file that I had cut and pasted, we need to give the paths for the train folder and the val folder inside of this file. All right, now we're ready to train our model. But before we actually train, we need to install Ultralytics. So if you have already installed Ultralytics, if you were following some of my previous videos, if you have installed Ultralytics, it will just tell you that you already have it on your environment. But if you're new to this, please install Ultralytics. And next, we're just going to run this code here. And there's a small adjustment I need to make to this code. The name of the model needs to be changed. I'll actually go ahead and look that up really quick. So you can very easily find the name of the model by going to the GitHub page for Ultralytics and scroll down to where it says segmentation. Oh, I missed it. It's up here. So pick the model that you want to run. I'm going to go with the medium-sized model. It's a Yolov8 M. And I'm going to copy the link, paste it into a new tab. And this last part is the name of the model. So model took about 0.118 hours to complete, which is very quick. I only did 200 epochs. So it's not going to be the best predictions, but it's just fast. In the results folder, there are multiple graphs that tell you how good of a training has been accomplished. If you're interested in the model performance, you can take a look at those. For this demo purpose, I'm not interested in that. I'm just going to move my best trained model and rename it in the root directory. Okay, now that we have a model trained, I'm going to go ahead and utilize this to run a video analysis. I have a script that I made and I have uploaded it already to my GitHub page that I'm downloading right now. So within this, there are a couple of things we need to input into the script. The model, the trained model's path needs to go in. And then the video. So I have a small 60-second clip that I'm going to run. Otherwise, it would take a whole lot of time. Okay, so for me, these are the things I need to change. There are ROIs that you can create further down the script. And if you're interested in making different ROIs, you can always just put in the region of interest coordinates, and you will have your different ROIs. So the way to run this script is just type in Python and the name of the script, and it will start running. Because it's a 60-second clip, it's going to be really, really fast for me. So there are a couple of files that get generated, and then in the terminal there are some data outputs that are printed out. So for example, ROI1, it has entries, exits, average, frames that were spent in that ROI, and so on. And then for the video output, you get a video that looks like this, with the mouse and the center of mass for the mouse being labeled directly on the video. So currently it's not very accurate. There are a couple of things we can tweak within the script to make it a little bit more accurate. And there's one trick I guess I should show you right now. So scroll down in the script and you can see this IOU being commented out. You can just copy and paste it into the results just like that. And this will help minimize some of the false positive Let me show you. Let's rerun the same video. So with this, you can see there is considerably less number of entries and exits. And in the video frames, you can in fact see that there are not so many multiple instances of center of mass. The other way to speed up the accuracy of your model is, of course, by giving it more training data and training it on training for a longer period of time. In the Excel file that gets generated, there are X and Y coordinates for the center of mass, but at the very end there are these ROI data sets. So you can of course graph out your X and Y coordinates, and each column corresponds to the following. Alright, so the next thing I want to show is that this script is compatible with Colab, and you can run this in Colab as well. You just need to modify some of your paths to the models and those type of things, and you can do that very easily. And here I'm running the same script that I just showed you. I'm just doing a few seconds of this video. And you get pretty much the same output as the script on the local GPU. Alright, so that's it for this demo. I hope you guys find this useful. If you have any questions or comments, please let me know.